Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And in today's lecture, we are seeing some question bank tutorial on the module 4, which is CFD techniques. Okay, in the previous session, we have seen about module 3, which is basically basic discretization methods using finite difference. So in the module 4, basically what are the CFD techniques which are available in the CAD we will be seeing, and mostly major important techniques would be like time dependent and space dependent schemes. So what are those strategies and how they benefit for the numerical simulations we will see. Okay, so the first part, so build an expression for Crank-Nicholson technique and explain its advantages in the field of CFD techniques. Okay, so first, basically, we will see what is Crank-Nicholson technique actually. Okay, so and next after that we will see what are its advantages in the CFD. Okay, so basically, the other name of Crank-Nicholson is semi-implicit scheme. So basically, it is called semi implicit. Okay, so this is called a semi implicit scheme. So why it is called semi implicit scheme, what is implicit and what is explicit? So let us take one example and see what is implicit and what is explicit scheme first. So let us take a 1D unsteady diffusion equation, so which is dou u by dou t is equal to alpha dou square u by dou x square. Okay, so this is a 1D unsteady diffusion equation. So let us write basically what is explicit and what is implicit. Then we will go for what is semi-implicit and see which is also known as Crank-Nicholson technique. Okay, then we will see what are the advantages in the CFD techniques. Fine. Okay, so first basically the explicit method. So in the explicit method, so their unknowns will be in the less count and the known values will be in more count. So basically, explicit method is a straightforward method. So where the values of number of unknowns will be very less compared to knowns, and it is very straightforward and easy method and simple substitute and get and go method actually. So that is explicit. Okay. So here if you see explicit, for the explicit, so how do we discretize this equation one is, so we will write index notation where u of I to the power of n plus 1. Okay, so the first term is u of I to the power of n plus 1 minus u of I to the power of n. Okay, so divided by delta t. Fine. So u of I to the power of n plus 1 minus u of I to the power of n divided by delta t. So this is for the first term of the, like, the left hand side term. So this will be common for both explicit and for both implicit. Okay. Now basically the alpha will be alpha. So the diffusion coefficient here. So we have dou square u by dou x square. So in the module 3 we have seen basically how to write down the finite difference equation for dou square u by dou x square term. So we will write that first. So u of I plus 1 minus 2 u of I plus u of I minus 1 divided by delta x square. So this is what we have. Now for the explicit method, so these RHS terms, so basically all those are known values. So we will keep or n. Okay, so that is what the meaning of explicit actually. So in explicit, so the only one unknown term we have. So here what is unknown term is u of I to the power of n plus 1. So the remaining terms, so which we have u of I to the power of n and u of I plus 1 to the power of n and u of I minus 1 to the power of n. So basically those values are the known values. So basically how many terms we have? So we have in explicit we have u of I plus 1 to the power of n and u of I minus 1 to the power of n. So first one, second one, and third one u of I to the power of n. Next, the fourth one is like u of I plus 1, sorry, so u of I to the power of n plus 1. So u of I to the power of n plus 1. So this value is the known parameter, this value is the known parameter, this value is the known parameter. So the unknown parameter is the fourth one. So basically here we have only one unknown out of four variables. Okay, remaining three are known variables. So which is coming under explicit method. Now we will see implicit method. So basically what is implicit actually? So for the implicit, we will write the same equation. Let us say dou u by dou t is equal to alpha dou square u by dou x square. Okay, so let us see implicit. Implicit. Okay, so for the implicit, so this first term here it will be same. So both for explicit and implicit method, the first term on the left hand side, so which is dou u by dou t, the time derivative term is same actually. So there is nothing change. So u of I to the power of n plus 1 minus u of I to the power of n divided by delta t is equal to alpha into, so u of I plus 1 minus 2 u of I plus u of I minus 1. So here we will put n plus 1, here we will click n plus 1, here we will use n plus 1 divided by delta x square. Okay, so here for the explicit we have only one unknown, for implicit we have more unknown values. So here let us write the explicit equation beneath of implicit equation. So we'll get to know u of I to the power of n plus 1 minus u of I to the power of n divided by delta t is equal to alpha into u of I plus 1 to the power of n minus 2u of I to the power of n plus u of I minus 1 to the power of n divided by delta x square. So you compare this equation with this. So what do we have? Left hand side terms. So here this one and this one, they are equal actually. There is nothing change. Now on the right hand side term, what do we have for the implicit method? So all the three parameters are unknown parameters. Whereas for explicit method, all the parameters which are known parameters. Okay, so we'll just compare and contrast here. So for implicit, let's say we have expressions u of I to I plus 1 to the power of n. Second one is u of I minus 1 to the power of n. The third one is u of I to the power of n. And the fourth one is u of I to the power of n plus 1. Okay, this is what we have. So this is for explicit. Let us take this is for explicit. Now for the implicit, what happened? Let us write the same. So u of I plus 1 to the power of n we have, and so here we have n plus 1. So second one is u of I minus 1 to the power of n plus 1. The third one is u of I to the power of n plus 1. And the fourth one is u of I to the power of I plus 1 to the power of n. Okay, so this is what we have. Okay, so here the only one parameter is known, which is u of I to the power of, there is one more parameter which is called, so u of I to the power of n. Okay, so this is what we have actually. So here if you see, Basically, here 1, 2, 3, and 4, 5 parameters are available different. Okay, but here for the explicit, so 1, 2, 3, 4, 4 different parameters are available. Okay, so out of these parameters, you can see 1, 2, 3, 4. So the fourth one is the only one unknown parameter we have. Okay, we don't know this. So first parameter we know, second one we know, and the third one we know. But whereas for implicit scheme, what happened actually? So first one is unknown parameter, second one is also unknown parameter, and the third one is unknown parameter. The fourth one is unknown. Only fifth one is a known parameter. So if you contrast, so basically implicit method with the explicit, what happened actually? So implicit method has more number of unknown parameters compared to explicit method. So therefore, what we have to do is, so we have to write down the equations at all the grid points, and we have to form in the form of matrix. So basically, let us say we are writing equation initially at location I. So next we'll write location at I plus 1. So next we'll write at location I plus 2. So for the implicit method, so we have to take all these three equations and frame a matrix form, which is A, which is X is equal to B. So X will consist of a matrix which has, let's say, you have the terms of U of I plus 1, U of I plus 2, let's say. So we have this matrix. So A is the coefficient matrix. So B is nothing but the right hand side term. So if it is 0, that will be homogeneous. If you have any source term, that will be non-homogeneous. So X is equal to A inverse B. So in this way, we will be solving in the form of inversion of matrix to get the values of flow parameters, or let's say the values at every grid point for the implicit method. So this is one technique. For explicit method, what we have, it's a straightforward, simple, with the initial values and with the initial conditions, you will get to know, so what is the value of the grid point at that location. Okay, so once we know the initial conditions, so we will use that and we will actually switch out, and we will get those values and substitute that. That is what we have. Okay, now let us come to Crank-Nicholson. So Crank-Nicholson, basically we have seen it as semi-implicit. So semi-implicit, and here you can see, so what do you mean by implicit? And we have seen explicit. So the meaning semi is, so that would be half implicit, that would be half explicit. Okay, we'll see the same equation again. So what is that equation? So we have dou u by dou t is equal to alpha into dou square u by dou x square. Okay, so for this we have to write the semi-implicit equation. So we'll write down here. So what happened actually? U of I to the power of n plus 1 minus u of I to the power of n divided by delta t. Okay, which is equal to alpha into, so here we have two things. One is called the switching factor. So we use a switching parameter which is called theta. So theta here we actually use it as a switching parameter. So if the theta value is 0, it switches to one scheme. If theta is equal to 1, it switches to other scheme. If theta is equal to half, it switches to another scheme. Okay, so let's see, basically let's write down what is the formulation and then see how does the switching factor varies for the theta. Okay, so theta into, so we have, let's say, u of I to the power of n plus 1. Sorry, so we have u of I plus 1 to the power of n minus 2 u of I to the power of n plus u of I minus 1 to the power of n divided by delta x square. So this is the one thing for theta. Okay, so there is one more switching factor plus 1 minus theta into u of I plus 1 to the power of n plus 1 minus 2 u of I to the power of n plus 1 plus u of I minus 1 to the power of n plus 1 divided by delta x square. Okay, so here you can see this is the first term on the right hand side, this is the second term on the right hand side. So you observe carefully this entire expression. So this is the generic expression, so which can divide the full form of scheme into half implicit and half explicit also. Let us take the cases for the theta. So when theta is equal to 1, what happens actually? So when theta is equal to 1, what happens? So the scheme, the generalized equation what we have written, so that will be fully explicit. Why? Because here you see, you substitute theta is equal to 1. So when you substitute theta is equal to 1, the second term will vanish off actually. The second term will go off. Okay? And the first term will remain. So basically the first term is explicit. So totally the generic expression what we have written, that will turn out to fully explicit scheme when theta is equal to 1. When theta is equal to 0, what happens actually? When theta is equal to 0, what happens? So the equation, the generic equation which we have written, that will be fully implicit actually. Okay. So when theta is equal to 1, so that would be fully explicit. When theta is equal to 0, that will be fully implicit. There is one more thing which is called theta is equal to half, semi. Okay. So when theta is equal to half, what happens actually? So it becomes, so this will be 1 by 2 and this becomes 1 by 2. So basically the switching factor when theta is equal to half, so basically this is called semi implicit. So when theta is equal to 0, what happens? It is implicit. When theta is equal to 1, what happens? This will be explicit. Okay. So by this we can see that the switching factor is able to switch one numerical scheme to other numerical scheme. Okay. So the advantages you can see the Crank-Nicholson scheme is like here it can combine the advantages of both explicit method and both implicit method. Why? Because if you take explicit method, it is very straightforward method. So the initial guess value and the initial value for obtaining the numerical simulation after a run is very straightforward and easy for the explicit method. Whereas for the implicit method, you have to invert the full form of matrix. So you have to actually do the inversion of full matrix. So therefore, it is difficult. Okay. So that is why people use actually a Crank-Nicholson scheme, which is of time derivative scheme, so which is second order accurate in space actually. Okay, and it combines the advantages of both explicit method and implicit method. So implicit method is very robust actually. Robust in the sense what? So even if you do small changes in the grid actually, let's say the spacing or you vary time step. So whereas when you do the changes either in time step or let's say time change or space changes in the grid, so automatically the simulation what do you say, it get adjust and the simulation will go on smoothly. Now for the explicit method, when you change the time step, so that actually will be conditionally stable. When you change this implicit method, whether you change delta t or delta x, so it is unconditionally stable. So no, like there won't be any conditions for the stability. So implicit methods basically they are unconditionally stable. Why? Because when you change certain parameter, so that can affect throughout the domain. So automatically all other parameter will get adjust itself. so that the stability is satisfied. Whereas for the explicit method, so when you change one parameter, so it the other one does not know that it has changed. So why? Because when you are solving equation 1, so whatever the changes you do in the equation 1 for the explicit method, that will be there itself. Okay. Whereas for the implicit method, when you are doing some changes in equation 1, the equation 1 is depending on equation 2, equation 2 depends on equation 3, let's say. So when you change equation 1, automatically 2, 3 get affected in the implicit scheme. But whereas for the explicit scheme, 1, 2, 3, basically those three are independent to each other. Okay, so that's why when you change some parameter in the explicit scheme, it does not get affected with the other two equations. So therefore, it behaves a conditionally stability scheme, whereas implicit scheme is unconditionally stable. Okay, so we have seen basically what is Crank-Nicholson scheme. So we have built an expression for Crank-Nicholson scheme. So that is like we have taken, so dou u by dou t is equal to alpha dou square u by dou x square. We have taken it. So and we have written, so basically the semi-implicit, which is Crank-Nicholson scheme, so which is of u of I to the power of n plus 1 minus u of I to the power of n divided by delta t, so which is equal to alpha into, so we have a switching factor theta into, so u of I plus 1 to the power of n minus 2 u of I to the power of n plus u of I minus 1 to the power of n divided by delta x square. So next we have plus 1 minus theta. So where you have u of I plus 1 to the power of n plus 1 minus 2 u of I to the power of n plus 1 plus u of I minus 1 to the power of n plus 1 divided by delta x square. So here this is what we have seen in the previous session. So where the Crank-Nicholson scheme, which is also a semi-implicit scheme, we have seen. So where we found a switching factor called theta. So basically theta, when it is equal to 0, so what happens actually, that would give us fully implicit. So when theta is equal to 1, so that will give us fully explicit. Next, when theta is equal to half, we have seen it as semi-implicit. Okay, so here the semi-implicit is nothing but the Crank-Nicholson scheme. So what is the advantage we have seen? So the advantage is whatever the explicit method advantage we have. So the major advantage for explicit method is, so basically the initialization is very easy to guess the initial value for the simulation. Let's say one iteration value is very easy and straightforward, and that would serve as an basically predictor. So when you do the explicit method, so when you get the initial guess value from the initial conditions, that would serve as a predictor. So the implicit method, when you give that one, so then it will serve as a corrector actually. So basically combining the advantage of implicit and explicit will give a method called Crank-Nicholson method. So this is what we have seen for the Crank-Nicholson method. Now actually we will see, so basically what is ADI method. So alternating direction implicit method ADI by sweeping x direction to obtain t at time t is equal to t by half. So and we will see additionally to this what happens along y direction also. Okay, so basically we have two things actually. So one is 2D diffusion equation, 1D diffusion equation. So when you see this question, so this is related to the 1D diffusion equation. Next, in addition to this, we will see 2D diffusion equation. Okay. So basically you take 1D, so what happens, let us see. So dou u by dou t is equal to same alpha into dou square u by dou x square. So this is 1D. Next, dou u by dou t, which is equal to alpha into dou square u by dou x square plus dou square u by dou y square. So this is 2D. So we have 1D and we have 2D. Okay. So we will write the ADI expression both for one dimensional and for two dimensional. So the ADI, alternating direction implicit. So the meaning is basically when you are running a simulation, so it will start from simulation, let's say t is equal to 0 seconds. This is the initial. Let's say you are going with a time step of 1 second to t is equal to 1 second. Okay, so this is the initial one and this is the final one. Okay, so the initial one t is equal to 0 seconds and the final one t is equal to 1 second. So the alternating direction scheme is dividing the full time step between 1 and 2 into two parts, two equal parts. Let's say this 1 and 2 is in between intermediate location I and I to 2. So basically 1 to I. So is, let's say, t by 2 and I to 2, which will be t by 2. Okay, so this is what we will do for the ADI scheme actually. So the ADI scheme, like alternating direction implicit scheme, is such a way that so we take initially for a time step, let's say t is equal to t half, let's say from I1 to I. So the x direction like as explicit. Okay, and once the time changes from I 1 to I to, let's say I to 2, so immediately the scheme switches to implicit action. Okay, so that is what happens in the ADI method. So in the ADI method, so whatever the scheme we have, so we are dividing into two equal halves. So one is in between time t is equal to 0 to t by 2. Other one is from time t is equal to t by 2 to, let's say, time t is equal to t seconds. Okay, that is what we will see. Okay, so let's see. So basically, let us take initially t value is n. So the intermediate t value is n plus half. Okay, so next the next time step will be, so this will be t of n plus half. So next t1, so the t2, the next one will be n plus 1. Okay, so in between n and n plus 1, so we are doing this actually. Fine, so this is what we get actually. So let us write down this equation for 1D. So what happens, so here we have dou u by dou t. So here this term, for this term, so we have u of I to the power of n plus half minus u of I to the power of n divided by delta t by 2. So this is what we have. Okay, so this is for the time step term. Fine. So how do we write for step term? So dou square u by dou x square. So this one. So first we will write actually explicit, then we will switch to implicit actually. So explicit in the sense what happens? So this term will be u of I to the power of n, u to 2 of I to the power of n plus u of I minus 1 to the power of n divided by delta x square. Okay, so this is what we have. Let us build the final expression. So u of I to the power of n plus half minus u of I to the power of n divided by delta t by 2. So this is what we have for the LHS term. And for the RHS term, what do we have? The same. So this is in between time t is equal to n to time t is equal to n plus half. So this is the first half of the ADI. Okay. So this will be u of I plus 1 to the power of n minus 2u of I to the power of n plus u of I minus 1 to the power of n divided by delta x square. So this is what we have for the first half. Okay. So we'll see what happens in the second half. So in the first half, what happened along x direction, we have used it as the explicit method. So already we have discussed that for the explicit method, so the initialization or to guess the initial value is very straightforward and it is easy to get those values. So that is the advantage of this ADI method. So initially we will use the explicit method to predict the value. Then we switch other time step to implicit, that is called corrector. So whatever the initial guessed or predicted value that we get from first half will be taken to the second half as an input and we correct it and we try, and for every iteration we will actually, for a given iteration we will solve sub 2 iterations such that we get an accurate value. Okay, so this is what the main motto of ADI. Okay, we'll see what is the second half actually. So same, so u of I to the power of n plus 1 minus u of I to the power of n plus half divided by delta t by 2 is equal to, so here what happens actually, so what is the unknown parameter we have? So that would be, so basically the implicit is u of n plus 1 actually. Okay, so u of I plus 1 to the power of n plus 1 minus 2u of I to the power of n plus 1 plus u of I minus 1 to the power of n plus 1 divided by delta x square. Okay, so this is what we have for the second half along x direction. Fine. So this is for the 1D. So basically what is for 2D we will see. So for the 2D, so is the full form of the diffusion equation. Okay, so when you see the 2D, so x direction basically we will change to implicit, y direction it will be explicit, or let's say x direction it will be implicit, y direction it will be explicit. So basically both two will be different. Okay, we'll see the two-dimensional equation. So, dou u by dou t is equal to alpha into dou square u by dou x square plus dou square u by dou y square. Okay, when you take 2D, basically you have to take I comma j index notation, already we have seen. Okay, so the first term we will write it as u of I comma j to the power of n plus half minus u of I comma j to the power of n divided by delta t by 2. This is the first term is equal to alpha into, so along x direction let us take it as explicit, along y direction let us take it as implicit. So what happens actually, so u of I plus 1 to the power of n minus 2 u of I to the power of n plus u of I minus 1 to the power of n divided by delta x square. This is along x direction. Now along y direction what happens actually, so if we add, so this would be implicit. So how, u of I plus 1, so this would be comma j, comma j, comma j. So this will be u of I comma j plus 1 to the power of half minus 2 u of I comma j to the power of n plus half plus u of I comma j minus 1 to the power of half divided by delta y square. So here you can see the given time step. So first half you can see that we have here as along x direction we have explicit, along y direction you have implicit. So when we take 2D equation of the ADI, the full form of equation is basically changed into two parts, half implicit and half explicit. Okay, so in the second half, so basically this will interchange. So what happens actually, the x direction will change as implicit and the y direction will actually go it as explicit. Okay, we'll see basically what is it. So that would give us u of I comma j to the power of n plus 1 minus u of I comma j to the power of n plus half. So this value will get from first equation divided by delta t by 2, which is equal to alpha into, so we have, so now along x direction we have to give it as implicit. What happens, u of I plus 1 comma j to the power of n plus 1 minus 2 u of I comma j to the power of n plus 1, next plus u of I minus 1 comma j to the power of n plus 1 divided by delta x square. So this is what we have. Okay, plus, so this is implicit along x direction. So this would be u of I comma j plus 1 to the power of n plus half, because this is the known value. Okay, minus 2 u of I comma j to the power of n plus half plus u of I comma j to the power of n plus, sorry, I comma j minus 1 to the power of half divided by delta y square. Okay, so this is what we have. So basically what happened, so here actually it is 3 by 2, so because already half is done. Okay, so that would be 3 by 2. Why? Because so in between like n and n plus half is done. So next so the next time would be, you can take it as 3 by 2 also. So which is of the other half. Okay, so whatever the time step we have here, or you can take it as half also. So instead of 3 or half. So this value we get from the initial first step. So this value will get from initial first step. So this value will get initial first step. This value will get from initial first step. Okay. So what happened actually in ADI method? So in ADI method, so initially the x direction is explicit, where the initialization is very easy, and we get the values along x. So the next step along y direction, the initialization is easy, so that in the next step we'll get what are the values along y direction. So within a full time step between 1 n is equal to, so t is equal to n to t is equal to n plus 1. So we will get full initialization along x direction and along y direction. Okay. So therefore the ADI method is basically doing a split method, where to guess the initial values along x we take it separately, to get the initial values along y we take it separately. Okay, so basically this is what the ADI scheme which we have seen. So in the ADI scheme, so what we have seen is the time step t is equal to n to n plus 1 is divided into two halves. N is equal to n, the t is equal to n, or to t is equal to n plus half. The next one would be t is equal to n plus 1 to n n plus half to n plus 1. Okay, so the two time steps which we have. So first time step along x direction, we have changed like x1 as implicit, y as explicit, and in the next time step we have taken x as, let's say, it is implicit and y as explicit. So in this way we have actually independently taken the guess values along x direction, along y direction. So this is the advantage of ADS scheme, which is alternating direction scheme. So in the next module, like we will see, so basically what are the doodle questions on the module 5, which is finite volume method. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.